So what we want to do is walk through a sample yo-yo problem before we do our yo-yo lab. So here is our yo-yo, and it has a mass of 0.078 kilograms. It's released from rest and allowed to unwind the length of the string 1.2 meters. So part A, draw a force diagram for the yo-yo as it's falling. So think through, all of this is the inside axis, this is the outside part of the yo-yo, and the string is wrapped all the way around there so that as it's falling, we're going to have like a string all the way out to here, and then there will be a tension here in the string pulling up, but the force of gravity will be pulling straight down through the center of the yo-yo. Part B, the axle has a minimum radius of that, so that'll be the radius of this inside value, and a maximum radius of that, that will be the radius all the way out to the edge of that. So if we want to find the average of that, then how do you find the average of anything? You're going to add them up and divide by 2. So I'm going to take 0.0, not everything divided by 2, but in this case, we only have 2 of them. So add up the 2 values, divide by how many values you have, and when we do that, we get 0.012 meters, okay? Part C, now use the 2 acceleration laws, a translational law and a rotational law, to derive the equation for the moment of inertia of the yo-yo in terms of A, G, capital M, and this R average that we calculated down here. So remember, our translational acceleration equation will be F equals ma, and if the yo-yo is falling, then won't the force of gravity be bigger than the tension? So we can say the force of gravity minus the tension equals mass times acceleration, which means that we can do mg minus t equals ma. Now, if we want to talk about the rotational acceleration equation, then we're going to say that torque is equal to I alpha equals Rf. And from that, we can say, well, this R is really that average that we found, and it is going to be the tension will be the force then. And then we can say I, and this A value is going to be A times R average. Okay, so we're substituting in to turn that into a linear equation. When we do that, we can solve both of these for the tensions then in order to get rid of that value. So I could say, well, this tension is going to be IA over R average squared. This tension is going to be M times G minus A, right? So take this to the other side, take this to the other side, and then factor my M values out. Now I can take that then and simplify that by solving for this I. So if I multiply both sides by the R squared, divide both sides by A, I'm going to end up with an I value. Let's see, multiply both sides by R squared, I'll have M R average squared. Divide both sides by A, that means I'm going to get a G over A minus 1. And if you think through that, then doesn't that follow the form of our moment of inertias, where I'm going to have some fraction in the front times an mr squared value. And that's how I'm going to get my moment of inertia. Okay, part D. If the yo-yo takes 1.05 seconds to fall, then calculate the acceleration. So I know my time is the 1.05 seconds. I know my initial velocity is going to be 0. We already know that the string length is that 1.24 meters, so we can say that's going to be the height. We know the mass of the yo-yo is 0.078 kilograms, although if you remember when we talk about kinematics, that mass is not going to make a difference. However, it will play into when we go to calculate the moment of inertia, right? And what else do we know? I think that's all we need. From there, we can take and say x equals vit plus 1/2 at squared, and that will give us our linear acceleration. So our height is going to be this 1.24 is how much it's going to drop. The initial velocity is 0. 1/2 of a times the time, which was the 1.05 squared. And when you do that and you solve for a, you get 2.249 meters per second squared. So that will give us our A value. Then to find our moment of inertia, we're really going to just take this I value and plug in the values for that to solve for it. So we have 9.8 over the acceleration, 2.249, minus 1, times the mass, 0.078, times the radius squared, which was this 0.012 squared. And when we solve that, we get a moment of inertia of 3.77 times 10 to the negative fifth. Now remember that our units for moment of inertia really follow the units in the equation here, where these two units will cancel out. This will be kilograms and this will be meters squared. So our units are going to be kilogram meters squared. So the next thing we want to do then is we want to talk about energy. Just before you release it, remember that the yo-yo is going to have a certain amount of potential energy as it's up before it unrolls and falls down. So in order to find that potential energy, I'm just going to use my basic U equals mgh. We already know the mass of the yo-yo is that 0.078. We know gravity to be 9.8, and we know the height that it's going to fall is that 1.24 meters that were given to us in the problem. So 1.24 meters. Because all of those are in standard physics units, then we can leave them that way, and then when we multiply those, we get 0.9479 joules is our value for potential energy. So once that all unrolls down to the very bottom, and right at the moment it hits the bottom, it's going to have a certain amount of kinetic energy, but it will have two kinds of kinetic energy. It will have the linear kinetic energy of it falling downward, but it'll also have the rotational energy of it unwinding as it's falling. So first off, what we want to do is find to calculate the angular velocity. The way that we can do that is by treating this like a linear problem and then converting it at the end. You could also convert everything now and then turn it into an angular problem, right away and do it all. It works either way, just getting there a different way. So 2 times a times x. Well, we know the initial velocity was 0. We are looking for that final velocity, so it's going to be 2 times the acceleration that it experiences. Now, remember, that's not going to be the acceleration of gravity, because we calculated the acceleration up here to be this 2.249 meters per second. So this will be 2.249, and the distance that it's falling is what we said earlier, that 1.24 meters of the string. And then we'll square root that. Once we do that, we get a final velocity there of 2.36 meters per second. Now, the problem with that is that it doesn't ask us for the linear velocity, it asks us for the angular velocity. So remember, we convert that by doing the angular is going to be the linear divided by the radius. So 2.36 divided by the average that we had up there is the 0.012, and we get an angular velocity of 196.8 radians per second. Next up, then, what we want to do is to calculate that translational and rotational kinetic energy. So remember that our K-trans is going to be the equation we studied earlier, which is 1/2 mv squared. So we can take 1/2 of the mass, which we said was 0.078, times the velocity of the 2.36 that we just calculated up here. So we have to know both of these, and then square that, and we get a K-trans value of 0.2172 joules. Then we can take and do the exact same thing only for our rotational kinetic energy, which is the 1/2 I omega squared, and plugging in our values, half of the I, which we found up there, 3.77 times 10 to the negative fifth, times the omega, which we found here, the 196.8 squared, and we get a rotational kinetic energy of 0.73 joules. And notice that more of the energy is stored in the object or in the yo-yo that is rotating than actually is in the energy of it moving. Now, was the energy conserved? So when we want to talk about conservation of energy, well, theoretically, the potential that we had at the top should equal the kinetic translational plus the kinetic rotational at the bottom. So we want to know, are those two values equal? So we have 0.9479, and over here for our translational we have 0.2172 plus 0.73, which gives us a 0.9473, and this is a 0.9479. So barring any huge rounding errors up here, we would say that it lost a little bit of energy, or you could argue and say, well, hey, there's got to be some error involved in that, and these are close enough, and you would just justify your answer by stating how you believe with that. So I want to show you one more common thing that goes with the energy, that a lot of times we will actually calculate the total kinetic energy and not do these individually. So I just want to practice with that, where we would say, hey, what is the total kinetic energy? It's going to equal the K trans plus the K rotational. So I want to derive an equation that's going to be this total kinetic energy. And if I do that, remember my translational is 1/2 mv squared. My rotational is going to be that 1/2 I omega squared. And if I'm deriving an equation, I'm not going to plug numbers in. I'm going to keep these as variables. So I'm going to keep this as 1/2 mv squared. I'm going to change this 1/2. Now my I value, remember up here, we found this I value to be what you have here. So I can substitute all of that in, G over A minus 1 times M times R average squared. That's all going to be in for the I. Then for omega, remember that we could convert that into a linear value by doing V squared over R average squared. So V over R and then squared because of the omega squared. So the beautiful thing about that is whenever you do that, then we have two radiuses there that both of those cancel out. So this one cancels out, this one cancels out. And if you look, I have a term 1/2 mv squared and 1/2 mv squared, which is literally going to be, I could pull a 1/2 mv squared out, and that'll give me 1 for this first term, plus the G over A minus 1 for the second term, because here's my 1/2, my M, and my V squared. Now, notice that my 1's will cancel out, so I can get rid of those 1's, and I end up with a value that is a total kinetic energy. And this is only for the yo-yo, by the way, because that's what our I value is for the yo-yo. So don't memorize this I value and say, oh, for everything, this I value is this. It's not. It's only for this yo-yo problem that we're doing. So then we can take and say 1/2 of G over A times mv squared, which is the same as saying G over 2A mv squared. And so we will have, that would be our derived equation for kinetic energy. So notice that that kinetic energy is still going to be some fraction of a coefficient times the mass times the velocity squared. And interestingly enough, if you want to, you could take and plug in these values where you'd say 9.8 over 2 times the acceleration, which we said was 2.249, times the mass, which was, somewhere I have that written down, 0.078, times the velocity that we calculated, the 2.36, squared, and you should end up very close, if not similar, to this value that we calculated the total kinetic energy to be, the 0.943. I think it comes off just slightly off of that from that. So that is one other thing that helps us a lot later if you just wanted to start practicing calculating those total kinetic energies. It's a way to combine it into one thing. Okay, for the last section here, what we want to do is we want to find the coefficient of friction once the yo-yo has rolled all the way down to the bottom, and now it's just spinning there, slowing down and slowing down and slowing down as it's spinning. So think through, at that point, the tension in the string is going to be going straight up above it, and then we're going to have a force of gravity that goes down. We'll have a normal force that goes up, that's going to be our tension. And then because it's slowing down, there's got to be a torque acting on this to slow down. And if you picture, it's right at the very bottom here on the edge of that small axis, where if this is rotating this way, it'll be a force of friction that is causing that to slow down. And that's going to be the force that causes it to decelerate or to slow down. So use the two acceleration laws, the translational and the rotational, to derive the equation for the coefficient of friction, mu, of the yo-yo in terms of I, alpha, G, M, and R. Okay, so the first one I'm going to look at will be the translational one. We'll set that up as F equals ma. And is this moving linearly at all anymore? And the answer to that is no. It came all the way down, and now it's just standing at the bottom here, spinning at the bottom. So there is no acceleration, which means that I can say the force of gravity minus the tension is going to be equal to 0. So the force of gravity has to equal the tension, and that means the tension is going to be mass times gravity. Now, the rotational equation, I'm going to take and do my torque equals RF equals I alpha. I can look at that radius and say, well, that has to be the minimum radius now. It's not going to be that average radius that we calculated up here. So it's going to be the minimum radius. The force that causes it to slow down or to decelerate angularly, we just said, is that force of friction. Now think through it. Isn't the force of friction equal to mu force normal? And in this particular case, what is our normal force? Well, our normal force is either the tension or the force of gravity, and they are both the same. So we can say the force of friction is going to be mu mass times gravity. From there, I can plug that in over here. So R min times mu mass gravity is equal to I. And it asks us to leave I in there. It also asks us to leave alpha in there. So depending on how it phrases the question, we could have had to take this I value and plug it in. We also could have taken this A and turned it into a linear acceleration where we would say A over R. But because the question asks us for both of those, we're going to leave it that way. So we're solving for mu. Mu then is going to be I alpha over RMG. And then just a quick double check to make sure that I have the right variables. I have I have alpha, I have an R, I have a mass, and I have a gravity. So it looks like that is going to be correct for my mu equation that I have to derive. So then the next part then will be in the lab, you measure A to be negative 51.2 radians per second. So determine the coefficient of friction between the string and the axle. So we can say mu equals, we know this I value, we can plug in that 3.77 times 10 to the negative 5. We know the alpha value because they give it to us here. It's the 51, I'm going to put a negative 51.2 radians per second. And that should be radians per second squared there, so that's a typo. Then we're going to divide that by the radius, which we said the minimum radius on this was, and here I have to find it on my sheet. All the way back up here. So our minimum radius was this 0.004004. So this is going to be 0.004 times the mass, which we said earlier was 0.078. And then technically speaking, because this is negative, our gravity is going to be going down the other direction. So it'd be negative 9.8, and that will give us a positive value when we calculate our mu. And when you calculate that, we end up with a value of 0.631. Remember that coefficient of friction does not have any units on it. And does that seem like a fairly legitimate value of mu? And you'd have to say it could be, because normally mu is between 0 and 1. And the closer to 1 it is, the more friction there is. The closer to 0 it is, the less friction there is. So between the string and that axle, there could be a pretty good amount of friction. So that, in a nutshell, is some of the different ways that we would apply angular motion to the falling of a yo-yo. For the moment of inertia, we would have our angular acceleration, we would look at the energy that goes with it, and we would look at the torque that goes with that as well.